Well, we can now have a look at the complementary sensitivity function, and for a tracking problem, the complementary sensitivity T is the one we should look at. Well, this complementary sensitivity function is the transfer function that links the set point or reference signal RZ to the output YZ, but it is also the transfer function that links N, the noise disturbance, to the output signal Y, although you'll have a minus sign that comes from here. So what we'll do is apply specifications on the closed loop, and what we'll do is impose these specifications on the Bode diagram of T, and what we'll do is consider the modulus of this transfer function, of this complementary sensitivity function, as a function of the frequencies. We have already seen that in the low frequencies, well, we want a small sensitivity, and we have achieved this by having the loop gain as high as possible in the low frequencies. If you do this, well, you will see that in the low frequencies you will have a large number divided by a large number, so this will tend to 1. So imposing a small sensitivity in the low frequencies corresponds to imposing a modulus of T that is 1, which is good because you will like to, or you would like to, follow the input reference signal, the set point, with a 0 steady state error. Well, this is how the complementary sensitivity function looks like in a Bode diagram. So what you see here is only the gain in dB, and you can see here that if at the 0 frequency omega we have T of e.g. 0, okay, so this is Z is equal to 1, is equal to 1, then we'll have a 0 steady state error. This is equal to imposing S in Z is equal to 1 is equal to 0, and this is also equivalent to imposing that there is an integrator in the loop, either in the controller or in the process. In this desired closed loop transfer function, the complementary sensitivity function, the frequency at which, well, you have the peak in the frequency response is the resonance frequency, and the associated gain is the resonance gain Q. The bandwidth frequency, omega B, B for bandwidth, is the frequency at which the gain of the complementary sensitivity is minus 3 dB, and what we call the bandwidth is the interval, the frequency interval from the 0 frequency to the bandwidth frequency. You'll find many definitions for the bandwidth frequency in the literature, but this is the one we'll stick to in this course. Well, you cannot look above the Nyquist frequency in a discrete time Bode diagram, and remember that the Nyquist frequency is related to the sampling period using the relation pi over Ts, and what we call the roll-off is the slope of the module of T above the bandwidth frequency omega b. We can now have a look at the specifications we can impose on the complementary sensitivity function. Of course, we have to impose that the module is as close as possible to 1, 0 dB, over the desired bandwidth. This will ensure set point tracking over the corresponding frequency range. We also have to make sure that the resonance peak or the resonance gain is under control. Above the bandwidth frequency, we have to ensure a sufficient roll-off. And the first reason we want this roll-off is that we want to be insensitive to high frequency measurement noise. Remember that the transfer function that links the input measurement noise to the output y is also the complementary sensitivity function, although there is a minus sign. The measurement noise has a high frequency content above the bandwidth frequency. So if we want to attenuate this measurement noise, we have to make sure that the complementary sensitivity function has a small gain above the bandwidth frequency. A second reason is that, well, we have probably not been able to capture the high frequency resonance peaks of the process in our model. So this means that there are unmodeled dynamics. Remember that the model is used to construct a controller, and if we push the bandwidth of the closed loop system, the bandwidth of the complementary sensitivity, too far, then when we'll use that controller on the actual system, we'll excite those unmodeled dynamics, and this is not desired. So what we'll do is, we'll not push the desired bandwidth too far, so that in reality we will not excite the unmodeled dynamics, and this will need a sufficient roll-off above the bandwidth frequency. What we have in this slide is a review of what we've seen in the previous slide about the measurement noise. So this is the closed loop system with the two inputs of importance, so the reference signal or the set point signal, and here the measurement noise, and the transfer function from the reference signal to the output is the complementary sensitivity function, but the transfer function from N, the measurement noise, to the output Y is also related to the complementary sensitivity function, although there is this minus sign over here. So if we look at this measurement noise, we'll see that it has a high frequency content. Well, it's a frequency content that is above the desired bandwidth frequency omega b. So we have to make sure that the complementary sensitivity has a gain that is sufficiently small above the bandwidth frequency. So we need a strong decrease, a strong roll-off of the module of t above the bandwidth frequency omega b. We'll look at the specifications in terms of the complementary sensitivity and the loop gain. So T, this is the complementary sensitivity, is PC over 1 plus PC, and the loop gain is PC over here. We have seen that if you want to track set point changes, we have to impose that the modulus of T is very close to 1 over a given bandwidth, that is the bandwidth of the closed loop system. We can ensure this by taking a high loop gain PC over this same frequency range, because PC will be large and it appears at the numerator and denominator, and therefore the modulus of T will be approximately 1. Well, we want also to enforce zero static error. Okay, so at the zero frequency in steady state, we have to impose that the modulus of T is equal to 1, and this can be enforced by including an integrator in the loop, and this integrator can either be in the process or in the controller. And remember that we had drawn identical conclusions based on the sensitivity function. At the zero frequency, we had imposed a sensitivity that had to be 0. Here, the analog frequency is considered, but this is the same as considering a discrete frequency as at 0, and this corresponds to z is equal to 1. Okay, so this is equivalent to imposing that t evaluated at z is equal to 1 in modulus is equal to 1. So we can kind of draw the same conclusion using the final value theorem. In order to achieve insensitivity to noise and robustness to unmodeled dynamics, we need a sufficient roll-off of t above the bandwidth frequency, or equivalently we need to impose a small module of t, so a module of t around 0 for frequencies above the bandwidth frequency. The complementary sensitivity function is Pc over 1 plus Pc. So if we impose a small module for the loop gain Pc, what we'll have here is a quantity with a small gain. So this one, the denominator will be approximately 1, and we'll have that the complementary sensitivity is approximately the loop gain in those frequencies above the bandwidth frequency. And again, this will ensure insensitivity to noise and robustness to unmodeled dynamics. We can look at those specifications visually in a Bode diagram of the complementary sensitivity, and we'll look here at the module of t. So the first thing that we have to do is to make sure that the module of t is approximately 1 over the bandwidth of the system. So this means that we have to squeeze t in such a way that indeed its module is close to 1 over a sufficiently large range of frequencies, and we have to make sure here that this resonance peak remains under control. Above the bandwidth frequency, we have to ensure a sufficient roll-off of t so that we are insensitive to measurement noise. Remember that measurement noise has a high frequency content, generally above the bandwidth frequency, and that the transfer function from measurement noise to output is also related to the complementary sensitivity function. So if we do not want to amplify the noise, but we want to mitigate its effects, we have to ensure that the module of t is as small as possible above the bandwidth frequency. We also have to impose this roll-off above the bandwidth frequency to make sure that we are insensitive to unmodeled dynamics, so parts of the process that we have not taken into account in our model. If we use that model and push the complementary sensitivity function too far, we could excite those unmodeled dynamics. So in the frequency ranges where we have unmodeled dynamics, so typically resonance peaks, we have to make sure that the complementary sensitivity function has a low gain. We can now combine with the specifications that we had on the sensitivity function. Remember that the sensitivity function is 1 over 1 plus Pc, right? And we had seen that typically in the low frequency ranges we want a module of s that is approximately 0. This is because the sensitivity function is a transfer function that links an output disturbance to the output. So by imposing that s in module is small in the low frequencies, we'll be able to have a good output disturbance rejection. But we have also seen that this sensitivity function is the sensitivity of the closed loop transfer functions in a tracking problem, in a low disturbance problem. So imposing that S in module is small will lead to insensitivity to variations in the process in our control problems, tracking and load disturbance rejection. We have seen that if we push here to have a better disturbance rejection and insensitivity to variations in the process because of the waterbed effect, well, the sensitivity will pop up at other frequencies, and this will lead here to a sensitivity peak. We'll come back to this sensitivity peak. We'll see that it's also related to robustness. So as usual, we have a trade-off situation. Although plotting a Nyquist diagram or a Bode diagram in discrete time is more complicated because we lose this fact that the transfer function is rational in j omega, and we have a relation that becomes like this. Well, the interpretation of the Nyquist diagram and the interpretation of the Bode diagram is exactly the same in terms of the gain and phase margins, and these have exactly the same meaning as in continuous time. So this means that you can recycle your knowledge from the course of fundamentals of control theory and apply it to this course. We will now look at the simplified Nyquist criterion, and this Nyquist criterion relies on the knowledge of the frequency response of the loop gain P times C that you can obtain either through modeling or experimentation. Well, in this simplified Nyquist criterion, we assume that the loop gain has no poles outside the unit circle. Okay, in the next slide that I will leave for your information, the case where there are poles inside the unit circle is treated. Well, assuming that the loop gain has no poles outside the unit circle, then the corresponding closed loop system will be stable if and only if the Nyquist curve of this loop gain does not encircle the point -1. -1 is the critical point. This means that the critical point is to the left of the Nyquist curve. So if we have a look, and this is the real parts, this is the imaginary part of Z, so this is the complex Z plane. We have the critical point -1 over here, and if, for example, we have a Nyquist curve of the loop gain that looks like this, well, the corresponding closed loop system will be stable, okay, because the critical point -1 is to the left of the Nyquist curve, and there is, well, the curve does not encircle the point -1 at all. So we'll have a look here at the phase margins and the gain margins in a Bode plot. Okay, well, you have to have a look at the loop gain PC. This is important because in the transfer functions that we're considering, we'll have a numerator and the denominator will be 1 plus PC. Okay, so we are looking at the loop gain PC, and we are kind of looking how far it is from the critical point -1. And in this Bode diagram, -1, well, this is really a gain of 1, 0 dB, and a phase shift of -180 degrees. This is the critical point. So let us look at the phase margin. For that, we look at the frequency at which the loop gain is 1, so 0 dB, and this frequency is called the gain crossover frequency. And if we go and look in the second part of the Bode diagram, well, we see that here we have some margin. We can still lower this phase Bode diagram before we reach the critical point. So we have a margin here that is equivalent to Vm. This is the phase margin. So we can now have a look at the gain margin, and for that we need to consider the frequency at which the phase shift is minus 180 degrees, and the corresponding frequency is the ultimate frequency, or the phase crossover frequency. And you can see over here that we still have some margin, so we can increase the gain before we reach a gain of 10 dB. So we have here a gain margin that is here in the Bode diagram in dB, so you can compute it with this relation in absolute terms. So the gain margin in absolute terms will be AM, and you can obtain it from the gain margin expressed in dB that you can read in the Bode diagram. In summary, the phase and gain margins can be obtained from the loop gain that you see over here, and they cannot be obtained from PZ, as I often hear at the time of the exam. So what you need to do is determine the gain crossover frequency, the frequency at which, well, the gain of the loop gain is 1, the ultimate or phase crossover frequency, and this is the frequency at which, well, the phase shift of the loop gain is minus 180 degrees. Once you have determined the gain crossover frequency, you have to have a look and determine how much margin, phase margin, you have before you actually reach the critical point, and this phase margin is obtained by this formula over here. Indicative values for the phase margin is, well, roughly in the neighborhood or in the interval 30 degrees to 60 degrees. And, well, the phase margin gives you the robustness to phase changes or delay changes in the control loop. So it tells you how much additional delay you can afford in your control loop before you go to instability. Well, once you have the ultimate frequency or the phase crossover frequency, the gain margin is 1 over the gain of the loop gain at that particular frequency. Indicative values are in the range between 1.7 and 5. So if you express this in dB, right, well, you have a range that is approximately, and again, these are indicative values, 5 to 14 dBs. Well, the gain margin tells you how much robustness you have to gain changes in the control loop. Well, we can also have a look and find the phase and gain margins in a Nyquist plot. Of course, again, we have to consider the loop gain, P of Z, C of Z, and what we'll do is look at the corresponding Nyquist curve. So we consider this quantity as a function of frequency, and this will be a complex number. What you can do is plot it as a function of its real part and imaginary part. So this is here the complex z-plane, and each point corresponds to a frequency. So what you have over here is part of the unit circle, so you can imagine the rest. And as you can see from the simplified Nyquist theorem, stability theorem, you can see here that this corresponds to a closed loop system that is indeed stable, because, well, the critical point is to the left of the Nyquist curve. We can start with the phase margin, and for that we need to find the frequency that corresponds to the gain crossover frequency, and the corresponding point will be the point where the Nyquist curve meets the unit circle. Okay, and at that frequency, well, you can see here that the gain, of course, it's the distance from the origin over here, is indeed 1. Right, the phase shift is, well, the angle that you see over here, so the angle that this line makes with respect to the real axis. So you can see here that at that frequency omega c, right, you still have some margin before you reach the critical point, and this is really the phase margin that is read here in the Nyquist plot. Well, to find the gain margin, you need to find the ultimate frequency or the phase crossover frequency, and at this point here, well, you can see that the Nyquist curve has a phase shift of a minus 180 degrees, so this point here corresponds to the frequency omega u, and at that frequency you can read the gain, and this is the distance from this point to the origin. Okay, so you can see that you have some margin, some gain margin, and this, well, gain margin is precisely the inverse of this distance over here, and this is how you read the gain margin in the Nyquist plot. Well, when you look at the Nyquist curve of the loop gain here in blue, you can read that the phase margin is Vm and the gain margin Am. Well, you can consider another case of a loop gain that is shown here in the dashed line in purple, where you have exactly the same phase margin and the same gain margin, but you can clearly see that this Nyquist curve comes much closer to the point, the critical point -1. So the second system has insufficient robustness, but it has, well, the same correct gain and phase margin. So we need another robust stability margin indicator to deal with this second case. We therefore have to introduce a new robustness criterion, and this criterion involves the shortest distance between the Nyquist curve and the critical point. We'll define the sensitivity as 1 over the shortest distance. Well, if you then look at the second case, you can see that this, well, shortest distance is smaller, and therefore we say that the second system has a higher peak sensitivity. Okay, so the sensitivity in the second case is higher than the sensitivity in the first case. Remember that, well, the sensitivity is 1 over the shortest distance, and as you can imagine, we call them sensitivity because they are related to the sensitivity function. Well, this sensitivity peak ms that we have defined in the previous slide is really the inverse of the minimal distance between the critical point -1 and the loop gain L. So 1 over ms is the, well, minimum distance between the point -1 and the loop gain, and so this is the minimum over frequencies of, well, this modulus, the modulus of 1 plus L, right? If you now replace the loop gain by P times C, this is the expression that you obtain, right? So we are interested in ms, and ms is 1 over the minimum over omega of the modulus of 1 plus pc, right? But this can be written because 1 over the minimum of 1 plus BC is the maximum over omega of this transfer function here, evaluated at z is equal to the exponential of j omega ts. But this is really the sensitivity function that we have defined previously. Okay, so we look at what frequency this sensitivity function is maximum, and we take the maximum gain. This is why this is called the sensitivity peak. Okay, well, this maximum of the modulus, and so the maximum over frequencies in the Bode diagram, the top part of the Bode diagram, is also called the infinity norm of the sensitivity function. Well, if you want to have a look at that, look at the course of linear algebra and applications. At the end of the chapter on applications, you'll see the definition of the H infinity norm. Well, anyway, the sensitivity peak is always larger or equal to 1, as you have seen in the examples that we have considered in the previous slides, and indicative values for the sensitivity peak are in the range 1.3 to 2. So if we have a look at the Bode diagram of the gain of the sensitivity function, well, you have to look for the frequency that maximizes the sensitivity gain, right? And this would be at this frequency over here. Okay, so this would be the sensitivity peak, ms, and this can be used as a new measure of robustness because it is linked to the distance between, the shortest distance between the loop gain Nyquist curve and the critical point -1. This subsection on performance specifications in the S domain is also treated in the course State Space Control Methods, where it's tackled with more details. In this slide, we review the second order system with complex conjugate poles. It has transfer function that is given over here, and this transfer function should look familiar because it's a review of what you've seen in the course of my colleague David Rouchard in his course of fundamental control theory. Omega n here is the undamped natural frequency. Zeta here is the damping ratio. It's a number in between 0 and 1, and you can see that the damping really is affecting what is called the damped frequency. If you complete the squares on this denominator, if you complete the squares on these two first terms, well, you construct a first square over here, s plus zeta omega n, and this will produce s square, this one, plus 2 zeta omega n s, and then you'll have also zeta square omega n square. Okay, and this zeta square minus omega n square you have to subtract, and so you end up with the second term over here. This is to show you that it's rather easy to obtain the poles of the system. Okay, and you could do this as an exercise. It's not that difficult. You can also compute the step response, and it is given over here. Well, as you can see, the real part of the pole is minus zeta omega n, and we'll call it minus sigma, and the imaginary part is really the damped frequency omega d. Well, if you use this expression that we obtain from the step response and you use it, for instance, in MATLAB Simulink, you can obtain a typical step response of this second order system with complex poles, and it's given here in green, and we'll use it to define a number of quantities that will be important in this course. The first one is TR, and TR stands for rise time. It's the time that is needed to go from 10% of the final response to 90% of the final response. TS is the settling time. It's the time that is needed for the response, the step response, to settle in a band of plus minus 1% of the final response. We'll use also sometimes the peak time, and this is the time for the first peak, and then we'll have also the overshoot, and the overshoot is expressed in percent of the final response. Okay, and this final response is given over here, right? And in the next slides we'll link these quantities with the important parameters, which are the natural frequency and the damping ratio zeta. Well, this is the dominant second order pole configuration. You see here that the pair of complex conjugate poles are over here, right? So the real part is sigma, it's omega n zeta. This is what we had obtained previously, and the imaginary part is the damped frequency, which is the natural frequency times the square root of 1 minus zeta squared. You can also see that this distance over here is omega n, the natural frequency, and that the damping ratio zeta is related to this angle over here by the relation theta is the arc sine of zeta. You say that this is indeed consistent, because if you're working in this right angled triangle, you see that this distance here, sigma, is indeed omega n times the sine of theta, okay, the sine of the arc sine of zeta, so you'll have omega n times zeta. So everything is consistent in here. You've seen in the course of my colleague that the rise time, overshoot and settling time are related to the quantities omega n and zeta. The rise time is 1.8 over omega n. So what is important here is that this rise time is in 1 over omega n. So if you want a rise time that is small, well, you should go in this direction over here, right? So this is TR that is becoming smaller. If you look at the overshoot, the expression is given over here, and you can see that when theta is moving in this direction over here, so if you push this down, right, then zeta will become closer and closer to 1, and you will see that if you would put a zeta here that is closer and closer to 1, because of this 1 minus zeta square, you'll have the exponential of something minus something that is large, so this will go to an overshoot of 0. So if you want to decrease the overshoot, you should push over here as I have shown. The settling time, right, this is really the time Ts that is needed in such a in order to have e to the minus sigma Ts is equal to 0.01. This is this 1% band around the final response, right? If you compute this exactly, this is what you obtained, but we'll use this approximation that was already used in previous courses. So the settling time is 5 over sigma, where sigma is the real part of the poles. So if you want to decrease the settling time, what you should do is, well, increase the real part. So you should go this way, and this will decrease the S, right? And this would decrease the overshoot. Well, we have just seen that the rise time is, well, influenced by omega n, the natural frequency, and if you push this way, well, you will decrease the rise time. The overshoot is related to this angle theta, which is indirectly related to the damping ratio. So if you push this way, the overshoot will decrease. And finally, the settling time, well, is related to the real part of the pole, sigma, which is equal to omega n zeta. So if you push this way, you will decrease the settling time. As you know, good performance is a mix between an appropriate rise time, an appropriate overshoot, and an appropriate settling time. So really, when you have good performance, the appropriate pole region for good performance will look like the intersection of those three regions, as is shown over here. Well, what you have seen previously is of course valid for the simple second order system, which means that you would have only two dominant poles to place, and we forget about additional poles and additional zeros. So in reality, things become a little bit more complicated, but what we've seen here can still be used as a guideline. So if you have a certain design, right, and you see that the rise time is too slow, what you should do is increase the natural frequency of the dominant poles. If the transition has too much overshoot, and when you do a step response, then you need to increase the damping of your dominant second order poles. And if the transition persists too long, in the sense that the settling time is too long, well, then the poles need to be moved to the left in the convex plane. Nevertheless, it is interesting to study the effects of an additional zero or pole, and this is what we'll do in the next slides. So let us have a look to the presence of an additional zero. So we'll consider a transfer function with the same denominator, and again we can do the completion of the squares. Sigma here is omega n zeta, and omega d is the natural frequency times the square root of minus zeta squared. Okay, so if this term disappears, we have the transfer function that we have considered before, but we have added this term over here. So this means that we have now still a unit steady state gain, right? The steady state gain can be obtained by considering S is equal to 0, right? If you consider S is equal to 0, it's easiest to see it over here. We see that we still have a unit steady state gain, and we have the presence now of this 0 in minus alpha sigma. So you see that when alpha is large in modulus, okay, you can see it over here, the presence of the 0 will have very little effect on the response, and this 0 will be very far from the two complex conjugate poles. If alpha is approximately 1, then the value of the 0 will be close to the real part of the poles, and a substantial effect can be expected, as you can see over here. And when the value of alpha decreases to 0, well, the influence of the 0 will further increase, as you can see over here. So what we'll do in the next 2 slides is use the expression of the step response to look at the influence of alpha. We'll consider 2 cases: alpha positive, right, and then alpha negative. And we will see that this corresponds to a system with an inverse response. We have seen this before, or you have seen this before in other courses. A good example is the lead lag system, and its transfer function is over here. If you look at the step response, it will look like this, at least if the lead is negative. Okay, so you could compute the response of the step response, but what we'll do is use the initial value theorem to compute y of 0. In the case of a step response, we'll have to take the limit when s tends to infinity of s times the response in the case of a step response. So we'll have k t lead s plus 1 t lag s plus 1 times 1 over s. The 1 over s and the s will cancel out, and this will lead to k t lead over t lag. Obviously t lag will be positive, otherwise you would have a lead lag system that is unstable, and well, it would make no sense to look at the step response. So t lag is positive, but you see here that when t lead is negative, indeed you have this inverse initial response. Okay, so at time t0 you will have something that will go down, right, before of course going to the value of k, because in steady state the gain will indeed be k over here. So here we have the step responses of the systems with a 0 in, and so the 0 is in minus alpha sigma, and you see here in blue, well, we have the response where alpha tends to 0. So basically this is the response, the step response of the transfer function without the 0. So it's this one over here. Okay, and as you can see, when alpha is large, for instance when alpha is equal to 10, there is very little influence in the step response, and well, the influence becomes larger and larger when alpha decreases. And when alpha is equal to 1, you're really in a situation where this is the complex plane, right, real part of S, imaginary part of S. So you would have your poles, for instance, over here, and the 0 would be right here. Okay, and you can see that if this is the case, well, the influence of the 0 will be quite substantial. So previously we have considered the case where alpha is positive. By the way, we have normalized everything in such a way that you can draw step responses independently of the natural frequency. In this case, we'll take alpha negative. The 0 is in minus alpha sigma. So this means that this 0 is to the right of the imaginary axis, and this is explaining why we see these inverse responses, these inverse step responses. Again, when alpha in modulus is large, well, the presence of the 0 is hardly felt, and when alpha is tending to minus infinity, well, you have the step response of the original transfer function without the 0. So this is this transfer function here. So when the modulus is decreasing, alpha is still negative, but its modulus is decreasing, you see that the influence of the 0 is felt more and more, and here you see this in this, well, inverse responses. The situation in green comes from the following case. So here you have the complex plane that is drawn, the real part of S, and here the imaginary part of S. So we'll assume as before that the poles are located over here, the complex poles, and the situation that corresponds to the green line is that, well, you have here the real part, sigma, you draw it over here, and this leads to a 0 over here, right? So the situation that is drawn here corresponds to this case over here. In the present study, we have taken zeta, the damping ratio, is equal to 0.5, and we have looked at, well, different cases of alpha to study the presence of an additional 0. And as you can see, there is really a large influence on the overshoot. Remember that alpha is equal to infinity corresponds to the response where there is no 0, and we know that for zeta is equal to 0.5, the step response in this case will give approximately an overshoot of around 16%. So what you see here is the influence of the additional 0 on the overshoot. Okay, and we consider three situations: zeta 0.3, zeta 0.5, and zeta 0.7 with the respective colors. You remember that when alpha in modulus is sufficiently high, and let's say that alpha is either smaller than -4 or higher than 4, the influence of the 0 is hardly felt, and indeed what you obtain, right, is the percentage overshoot that you would expect with the original transfer function without the 0. So with a zeta that is 0.7, you would expect something around 5%. This is indeed correct. 1, 2, 3, 4, 5. So this is approximately 5%. Zeta is 0.5. Well, we have seen this is approximately 16%. And with a zeta is equal to 0.3, well, this is approximately 35% overshoot. Okay, well, of course, when alpha is decreasing in modulus, so if you go in this direction or in this direction, you can see that the effect of the 0 becomes larger and larger, and of course it becomes, well, dramatic when alpha is close to 0. So we'll now consider the case of an additional pole, and again we'll introduce the pole in such a fashion that the steady state gain is preserved. We still have a unit steady state gain, and because this is a sigma over here, and we see here that the pole is in minus alpha sigma. Of course, here we only consider alpha positive because we only consider transfer functions that are stable. you can see that when alpha is going to be very large, this pole is going to be so fast that there will be hardly any effect on the step response. If alpha is close to 1, then the additional pole will be close to the real part of the complex poles. Okay, we'll have a situation that will look like this. So real part of S, imaginary part of S, the complex conjugated dominant poles, well, they will not be dominant anymore in this case, are located over here, and the additional pole is located over here. It's a real pole, and in this case, well, you can expect a substantial influence, and in this case, well, the major effect will be, of course, that you will slow down the system, and this will increase the rise time. So this is what you see here in this step response plot, where alpha gives you, well, the step response with different poles. Remember that when alpha is tending to infinity, well, this third pole is so far that you can neglect it, so the response here in blue is the one that you have with the original transfer function, that is the following one. And as you can see, if alpha is large, right, well, the effect on the step response is rather small, and then when the modulus starts to decrease, the effect on the response becomes larger. As you can see here, indeed, the system here in green that corresponds to the situation that I have depicted in the previous slide, well, is such that you have a much slower response. As we have said before, the rise time has increased quite dramatically. So here's a summary on performance and on how you can shape the dynamic response in the case of dominant second order poles. Well, for a second order system with no finite zeros, you can use the following rules of thumb. The rise time is approximately given by this expression here, and it's mainly influenced by the natural frequency. Here we have a series of overshoots that correspond, of course, to values of the damping ratio zeta, and the settling time Ts is approximately given by this equation, 5 over the real part of the dominant poles. Associated with this, you should have a look also at the region of good performance. Well, obviously, in most designs you have the presence of a zero or more zeros, a pole or more poles, and a zero either in the left half plane or in the right half plane will typically increase the overshoot if the zero is within a factor 4 of the real part of the complex poles. An additional pole in the left half plane will increase the rise time significantly if this pole is within a factor 4 of the real part of the complex pole.